Hey, Zuko.
Hi, I'm Zuko, and I'm going to talk for up to 20 minutes about spying and the least authority file system. So many years ago now, decades ago, I started worrying that in the far future everyone would be using the internet, and once everyone was using the internet, then large centralized powers would gain the ability to spy on what everyone was doing all the time. And I thought that would inevitably happen. I could try to intervene in this future history by inventing cryptography tools for people to use to protect themselves from that kind of surveillance. And it turns out I was right. That day has now come. As we've all learned by public revelations recently, almost everything that almost everyone does is being collected and processed by the computers of either spies or criminals or somebody. So let me tell you about the thing that I've been working on for a few years with a bunch of other open source hackers. It's called the least authority file system. I don't have slides, but if you look up that string on the internet, you can find the open source project. And I have a company that's commercializing it, but I'm not really going to talk about that because nobody likes to listen to sales pitches. But you should totally go to my company's website and give me money. And obviously what we decided to do when we set out was make it possible for people's data to be encrypted on the client side before it gets transmitted over the internet or stored remotely or whatever. And so the least authority file system is a storage tool, and it's called file system in its name because it has directories and files, so that you can organize your files into subdirectories and things like that. But the way you use it is more like, it's like BitTorrent that you can upload as well as download, rather than using it like a local file system that you like mount in your operating system. So it's a user space tool that people run, and then they use it like BitTorrent, but for both read and write, where BitTorrent is just for downloading, really. And you all already understand enough about cryptography that you can imagine how you could design such a thing so that all of the data gets encrypted before it gets uploaded and then gets automatically decrypted whenever someone downloads it to look at it. But we did some interesting things that I want to explain some of the unusual parts of the design. Well, before I do that, let me tell you a bit about the social context. It's this open source project. There's, like a dozen or an uncounted number of people who contribute patches and documentation and junk from all around the globe. There have been public releases of the source code for about 7 years now, and it's been pretty widely studied for a cryptography project. It's been used by like anonymous activists and people who won't confirm or deny that they use it when I ask them. I've spoken to 3 different people who won't deny that they work for the NSA and say that they're interested in specific uses of this file system. One of them who was working for the NSA left NSA and started working at Booz Allen Hamilton, and shortly after that, a few months after that, contributed a patch to the least authority file system to integrate it with Hadoop so that you could perform big MapReduce queries across your least authority file system stored encrypted data. This software is included in Debian and Ubuntu, so if you use those systems, then the easy way to get it is apt-get install it. So the interesting part of the design that I want to talk about today is that instead of the obvious thing of having sort of one encryption key per user and encrypting all of the data when it goes up and then decrypting it all when it comes down, we made one encryption key per file and also per directory. So every file and every directory has its own unique key that's separately, independent from all the other keys. And the reason we do that is so that you can do file sharing. So the least authority in least authority file system refers to this concept called the principle of least authority, which is that you should have and exercise only the minimal amount of authority that you need to get your job done. And so the fact that the storage servers that are holding everyone's data in the system don't have access to the encryption keys, that's an example of the principle of least authority, which is that in order to do their job of storing data, they don't need the ability to view the content. And so the system deprives them of that ability because of the principle of least authority. And it's that same principle that made us do this unusual design decision of making a different independent key for every file, because now you can give someone access to one file without giving them access to any other file. So any friend that you want to share with, or any person you want to share with, you can give them the access keys to some subset of your files, and doing so doesn't imply anything about all the other files, and that's an example of the principle of least authority. You're granting to those people the authority to read those files and no more. So that sounds like a really problematic design decision, because the problem with all of cryptography is key management. And that's why normal people don't use cryptography if they can help it, right? Anybody who sees two tools available, one of them says this is the secure tool, and the other one says this is the get your job done tool. Everyone knows to avoid the secure tool at all costs, because it'll impose hassle, it'll slow you down. Sarah was talking about earlier how when people realize that they have to deal with security, their brains turn off, like, oh God, not this again. You know? So, and the problem with cryptography in particular is key management. So, at first blush, it would be a terrible idea to multiply the key management problem by 1,000,000 times by making maybe 1,000,000 keys instead of one. And so then there's the other weird thing that we did to try to combine with that, which is that this is a file system with files and directories, and you can have directories within directories and so forth. And in any file system, Unix, Windows, if you treat like the World Wide Web as a file system, because there are like links that you follow, and when you follow the links, you come to new data at the other end of the link, all that stuff. In any such system, there has to be a file handle. There has to be a link that your computer is using to reach the document you're asking for, you're requesting. Okay. And the trick that's the most interesting and important concept in the least authority file system is we took all of those millions of encryption keys and we put the key for each file in the handle that references that file. So, like if you're familiar with a Unix file system, there are inodes, right? And the inode is not the file, but you pretty much never look at a Unix file without going through its inode on the way to it, okay? So what we did in the least authority file system was put the decryption key for that file in the handle, or the equivalent of the inode. And the effect of that is you're navigating your file system, like if your friend sends you a link and says, hey, look at this, and you like click on it. Or if you are CDing in your directory, like CD/MP3, CD/space, grep, or whatever. Every time you're navigating through the file system, your computer is acquiring the decryption keys necessary for any next step that you would take in the file system. Okay? So that is the big idea in the least authority file system. And I think it's potentially a big idea because it hides the whole key management problem. It makes it go away, because in a normal encrypted storage system, you basically have to do two things every time. You have to acquire the data, and you have to get the key or the access permission to access the data, right? So if you have some data in a normal unencrypted system, and you want to share it with someone, including like yourself on a different device, then you send a reference to the person you want to share it with. You say, hey, look at this, here's a link, or I copied this to you or whatever, however it is that you share. And in a typical secure file system, you double the hassle factor. Anytime you want to share something with someone, you have to send them the data, and you also have to send them the key. And what we hope is valuable in the least authority file system design is to reunify those two actions again. So in that design, when you want to send data to someone, you just send them this thing, which is the file handle, and that thing contains both gives them the ability to acquire the data, and it gives them the decryption key in one act. So there are a lot more sort of interesting parts of the architecture of the least authority file system, which I don't have time to go into now, but you can read about on our website. And I'm going to go back to the topic of spying that I started with, and then stop for questions. When, a generation ago, like when we were kids, police work and espionage were something that required manual effort. And manual effort is expensive. So when we were growing up, a typical person would be justified in thinking that nobody was spying on them because they weren't worth the effort and the expense of being spied upon. And sometime between now and then, that's reversed. And now spying is done automatically by computer programs that use, automated data collection and machine learning. And in that situation, it would require expensive manual effort for anyone to choose to not spy on you, to program the computer to exclude you from being part of the machine learning algorithm would be a complicated, expensive operation for him to do. So it's reversed, and now everyone is spied on, and you should assume that the information that you emit about yourself onto the internet is being automatically collected and processed. So this tool was invented and is currently being worked on as in large part as a political act. Like, the theory is that it's a dangerous situation to have automated surveillance of everyone by computer programs. And it's going to become more dangerous in the near future when those computer programs gain the ability to act on people as well as to surveil them. The example that I think of is the way your credit card company might call you if you make a purchase from a weird location or a weird kind of purchase. There's no human involved in that process. There's a computer program running a credit card company that evaluates the pattern as being unusual, and it can stop the transaction from happening without any human knowing that it did that as a fraud prevention technique. And that kind of automated intervention in the world is likely to come in the near future as a follow-on to today's automated surveillance. So especially in less free societies than here, you can easily imagine that in the near future, those computer programs will intervene, for example, to prevent people from communicating with one another if their machine learning algorithm has concluded that those communications are banned political speech, for example. So this least authority file system is intended to make it infeasible to surveil and censor people's communications indiscriminately on a mass scale, to do that to everyone at once. But it is not intended or believed that if you use this, that prevents you from being personally targeted. If you are a spy, or if you are being targeted by criminals who have chosen you to attack, or if you're traveling in a war zone and you are being attacked by cyber soldiers or something like that, then you shouldn't expect that this sort of technique of running encryption software on your client is going to be sufficient to protect you from that. But that's not the goal of this project. It's to allow people to be free of automated, indiscriminate surveillance. And that is my whole talk. It's been about 15 minutes. So now I can answer questions for a few minutes, if you have.
Okay, I have two.
Okay.
One are the keys for the encryption static stored in the inode for the length of that file's lifetime?
That's a really good question.
And two, if you can rotate them, is there a way to rotate it in a mass way to go through and basically just re-encrypt the entire hard drive with new keys? Or can it be done one at a time?
Yeah, so the questions are the keys static for the lifespan of the file or thing? And what is it like to rotate them? The answer is this is a weak spot in the architecture. Well, it's also kind of a fundamentally hard problem for the distributed case. I didn't really emphasize this, but this is not like just one hard drive with an encrypted file system on it. It's like a peer-to-peer network, like BitTorrent, in which many sort of ad hoc servers could be holding pieces of the ciphertext. And so in that context, it's you can't necessarily rely on the servers to forget the old ciphertext, right? Once you've encrypted some data with a given key and you've uploaded it to these servers, you could later ask them, you could say, oh, you know that thing I encrypted earlier, will you delete that ciphertext? And here's some new ciphertext instead. But you can't know if they really deleted it.
Fair enough.
Right? So it's kind of fundamentally hard, and our current solution is pretty weak, which is just kind of the obvious thing that the keys are static for the lifespan of the object. And if you really want to, so if I make a file and I share it with several people, and then I change my mind and I think, oh, I want to stop letting her see what I write in here, right? Then the only thing you can do with the least authority file system right now is make a new one.
Just thinking.
Copy your diary or whatever from the old one to the new one, and then share the new one with 3 people and exclude the 4th person from your new one. And that's too bad because that's like complicated and inconvenient, and inconvenience is like the death of security, right? So it's a concern for me. But also in the distributed case, it's almost impossible to do better. It's really a tricky problem. That's a good question. Thanks. Okay, do y'all have any more questions? I want to tell you something else. Because I have like 3 more minutes. Yeah? There's a cool hack that we did, which is sort of like what you see in Git, the distributed revision control system, which is that some of the things in the Tahoe file system are immutable by construction, which means that the handle that points to those things contains the secure hash of the contents of the thing, right? You know how this works in Git? How there is a tree or a chain of files and commits. So when you add new commits to the Git revision control system, each one has a secure hash of the previous one. And by the nature of the secure hash, you can't come up with a different file that will have the same ID. So in the least authority file system, we have both the Git style immutable files and more traditional normal mutable files. And that turns out to be useful to people in practice because of the principle of least authority again. Sometimes sometimes you want to get information from someone, and you want to know that the people who gave it to you, can't subsequently change it. So it's kind of like just sending the contents of the file, but it doesn't require bulk data transfer. You can still just send the thing. And you can have a directory tree that's immutable, and all of the subdirectories and files within that are likewise immutable. So that's another way of the principle of least authority is if you don't need the person to be able to update it, then you can deny them that ability.
How is that any different than read-only effectively?
Yeah, that's a good question. The question was how is immutability different than read-only? And they're related but different. So in the least authority file system, there's either, immutable thing is immutable, and the immutable thing can't be updated by anyone, not even the creator. Like no one in the world can ever update it. The mutable things you can have either read-write access or read-only access to, right? So, sometimes you want to give someone read-only access to a thing that you can continually update. Other times you want to give someone access to a thing that nobody can update. It's just really useful, especially for like tracking down what the hell happened ex post facto. It's really useful to say, this set of files cannot have changed at any point since they were created, so that we can exclude those having been tampered with or accidentally changed from trying to figure out what the hell's going on. Okay, thank you all for listening. Oh,
One more question.
Yay!
You were talking about that, and are the keys of the subtrees and subfiles and directories in any way derived from the previous ones?
Are the keys of the subtrees or subdirectories derived from the parent directory? It's a really good question. We actually are trying to work on this crypto idea that would let the keys be derived from the parent as an optimization. But currently, we use the simpler idea of the keys of the children getting embedded inside the parent, so that when you're navigating through, you can find them. One consequence of that is that you can't give someone a parent directory while denying them access to all of its children. So there's no way, which is kind of, I like it. It means that there's no like access denied error in the least authority file system. Like if you go into it, you CD into a directory, and there's a list of subdirectories.
You already have access.
You can CD to any one, and there cannot be an access denied error at that point. So whoever gave you that parent directory, if they didn't want you to have access to those child directories, they needed to give you a different parent with fewer children. Yeah, I like it. And so far, no users have complained about that limitation, so it seems to work.
Is a file being can you apply it to a directory and everything underneath it, or if you apply it to a directory, can you then change some files underneath this file?
Right, good question. And the answer is that the immutability and the read-onlyness are both deep properties that apply to all children transitively. So if I give you an immutable directory, I know that you can only ever access immutable. You and I both know that you can only ever access immutable things no matter how you navigate within it. And if I give you read-only access to a directory, you can only get read access to anything within it. I also like that property. That's cool. All right, any more questions? Okay, thank you all for listening to my talk.